All right, we are going to wrap up equilibrium. We've talked about equilibrium, the fundamentals around equilibrium. We looked at it within the context of acid-base chemistry. So we're going to talk about equilibrium for some other reaction classes. So remember, we've defined solubility, right? What makes a compound soluble by its ability to dissociate into its ions, right? Dissociate or ionize, like we see with table salt, right? If we add it in water, we see it ionize, and we say that's what makes a compound soluble. And we define insoluble as ionic compounds that don't dissociate when placed in water. But in reality, so this is how we're defining insolubility, but in reality, even insoluble compounds do dissolve to a small extent. They dissolve to a small extent. And they develop this sort of equilibrium between the solid and its dissolved ions. So we call insoluble compounds really sparingly soluble compounds. So here's an example of silver chloride that is a solid, and when placed in water, it will slightly dissolve to silver and chloride ions. So we have this equilibrium that exists between precipitation when the equilibrium shifts to the left and dissolution when the equilibrium shifts to the right. So we describe this equilibrium using equilibrium constant K. In this case, it's called a solubility product constant, right? So remember, K is always what we use to describe equilibrium. KSP has to do with solubility product constant. So it's equal to the concentration of the two ions, silver and chloride, because we neglect solids from our constant expression. So we can calculate the solubility of a compound from its KSP, and we call this molar solubility. We can also go the other direction where we calculate the KSP if we know the molar solubility of a compound. So let's think of an example. If we have barium sulfate, how do we expect that the solubility would compare if barium sulfate is dissolved in water versus 0.10 molar sodium sulfate? So pause this video and think about it. Will it have the same solubility? Will it dissolve less or more in water compared to sodium sulfate? So in pure water, we'll have this equilibrium between barium sulfate, the solid, and its dissociated ions, barium and sulfate. Now, if we place it in 0.10 molar sodium sulfate, we'll still have these barium and sulfate ions, but we'll also have sodium and sulfate ions as well. And so, because we have more sulfate ions in solution when we dissolve it in sodium sulfate, the equilibrium is going to shift to the left. And so we'll actually see barium sulfate precipitate out. So going back to our question, right, this means that the solubility in sodium sulfate must be less than that in pure water. It must be less than that in pure water because we've shifted the equilibrium to the left, to the solid barium sulfate. So this is described as something called the common ion effect, right? That states that if we take a solid, compare with it dissolving or placing it in pure water, the solubility In another ionic compound that has a common ion, let me rephrase. So the common ion effect basically says if we take an ionic compound and we dissolve it in an aqueous solution that has a common ion, it will be less soluble in it because we have this common ion that's going to shift it towards precipitation, in the direction of precipitation. So in this example, our common ion is sulfate. So sulfate is the culprit or the reason that the equilibrium shifts in the direction of precipitation.